Hi. So today we're doing probably my absolute favorite activity for the whole quarter because it's chemistry and I like chemistry. I like physics too. But I like modern physics a little more than classical physics. Anyway, I like chemistry and I like showing chemistry to you guys. It's kind of fun, but I'm not going to be there today. So I'm going to trust you guys to behave yourselves. So I want to show you an analogy. Let's say we're here in my sewing room. My sewing machine back there. I actually have two sewing machines. But anyway, say I'm going to sew something, right? So I have to buy ingredients. So I'm going to spend $2 and I'm going to buy a piece of fabric. Ooh, let's buy this one. It's purple. The other one was pink. I don't really feel like buying pink fabric, even though I already did. So here's my piece of fabric I'm going to buy. And let's say I'm going to take and I'm going to cut and sew this piece of fabric. I'm going to make these cute little mouse. He magically changed color. Okay, so we've got this cute little mouse. And I'm going to sell this cute little mouse. But unfortunately, the mouse market isn't very good. So I'm only going to be able to sell him for $1. So I get $1. But now I lost money on this deal because my materials cost more than my product. That happens sometimes, unfortunately, in industries, and it makes industries go under. Sometimes, though, let's say I'm buying the same $2 for the same piece of fabric. But now all of a sudden, people think that cute little fabric mice are just the best thing ever. And I all want cute little fabric mice. So I'm able to sell my cute little fabric mouse for $4 this time. $4. I have $4 and I made $4 because this time my ingredients did not cost as much as the product. And this is the way industry should be. I guarantee you the ingredients in pretty much anything you buy at the store does not cost as much as whatever you're buying at the store, or else the company would go out of business, right? Like that doesn't work that way. So what in the world does this have to do with chemistry? Let me show you. Guys, I'm sick. Let me show you. I'm gonna pop over to the this. We're gonna show you on this whiteboard here. You didn't really want to see my face. Oh, look, it's still there. That's great. All right, so let's pretend I want to make water and CO2. Okay. I feel like making H2O plus CO2. I'm feeling like cooking that stuff up today. Now, where am I going to get the H2O and the CO2? Well, let me tell you. We know that mass is conserved. I've been teaching you that energy is conserved, but mass is conserved too. And so you can't just magically like poof, we're gonna get some hydrogen atoms from magic. No, like they've got to come from somewhere. And where they're going to come from today is we're going to have some methane. We're going to have some carbon and a lot of hydrogens actually. And we're going to mix it with some oxygen. And what happens is we're going to put some money in, but not money. Chemical money is energy, actually. So we're going to put some energy in, just a little bit of energy in. Okay. So we're putting in a little bit of energy, just a wee bit of energy in the form of a spark. And it's going to like rip these ingredients apart. So I've got a C kicking around and I've got 4 H's kicking around. So I have my ingredients just like my fabric, right? Paid some money, got some fabric, paid some energy, and I got some atoms that are all broken apart. They're not stuck to each other anymore. And what happens is they form back together. We're not going to go into a lot of details on how. Take honors physical science next year. I'll tell you how. But what we end up with is 2 water molecules. Oh, we need 2 oxygens over here. And 1 CO2 plus. Now, these cost way less than the ingredients. So I get a lot of energy out. What this reaction is the burning of methane. Okay, so methane burns. I get water and CO2, but I also get a lot of heat, right? When you burn methane, you get heat out of the deal. Okay. So there's my fire. Someday, guys, like I said, if you really work at it, you too will draw as well as I draw. Anyway, this is what's called an exothermic reaction. That is a big word. And let me tell you how I remember exothermic. Well, thermic means temperature. What do I measure my temperature with all stupid day long today? Is my thermometer. It measures my therms, measures my temperature. Exothermic. Let's dissect this word. Well, therm means heat. Exo. What does that sound like? It sounds like exit. So we have heat exiting this system. You know, the exit. It exits the system, and you can roast your marshmallows on it, right? Like, or cook a barbecue thing on your methane. We usually do propane, but methane's the one I have memorized. But you know what I'm saying? You get heat out of the deal, and this is awesome. That's an exothermic reaction. Well, not all reactions are exothermic. Just like I don't always sell my little. Lost my mouse. Anyway, I don't always sell my cute little fabric mouse for more than I bought it fabric for, right? Sometimes the market goes down. What do we call an endothermic reaction? There are other endothermic reactions, and I'm not going to go through the particular chemistry of them, but one of them is baking soda and vinegar. Yeah, baking soda and vinegar, and we all know it makes bubbles, right? So we have baking soda. I don't remember the formula for baking soda. I am so sorry. It's just going to abbreviate it. I'm not going to abbreviate baking soda. So baking soda. We get baking soda. We get vinegar. Now we don't realize it, but we still have to put heat in to break these bonds apart. In order to get those atoms away from each other, you have to put energy in. Whenever you break atomic bonds, it always costs energy because it's like you're buying your ingredients. Think of it like breaking open a pack of whatever. Like if I want to make something here in my craft room, so I'm looking for crafts, I break open, breaking open a pack of fat quarter pieces. These are called fat quarters. It costs money to break those things apart to be able to use them, and it costs energy to break apart the atoms in the baking soda and the vinegar. And then what I get out is I get carbon dioxide, I get water, and I get sodium acetate, which again, I don't remember the formula for sodium acetate. I am so sorry. I don't feel like going and looking it up because I'm sick. Anyway, acetate. Okay, so I have carbon dioxide, bubbles. You guys know what bubbles. Yeah, water, and I get sodium acetate. But on this one, it takes a lot of energy to break those bonds. And it only releases a little bit. It always, Kate. So it always costs energy to break bonds. And it always releases energy when you form bonds. But the energy that it costs to break these bonds is a lot more than the energy that it takes to make those bonds. So what happens, this one got hot. What happens is that this one gets cold. draw me a little ice cube here. It doesn't actually freeze. I just don't know what else to draw to indicate coldness. So draw me an ice cube. Okay, so there's an ice cube because it gets colder. So if this is exothermic because the heat is exiting, this is called endothermic because the heat is entering. And you think, where does it get that heat? Where does it get that heat from? Well, there's water in the solution, and it gets the heat usually from the water. And in like the exothermic, it puts that heat into the air. Endothermic, it gets the heat from the water or maybe from its environment. If you touch an endothermic reaction, your hand will feel cold because it's taking heat out of your hand. It is taking some of this heat right here. This is energy, right? It's taking some of that energy out of your hand, and your hand is going to get cold. So, and this is so cool because except when it's endothermic, then it's hot. Oh, guys, I'm so sorry. So, it's really cool though because it's always this way. Anytime you form bonds, it gets warmer. Heat is released, and anytime you break bonds, heat is consumed. So I want you to think about like Christmas caroling. It's Christmas time and people go Christmas caroling. And it's actually warmer if you go Christmas caroling while it's snowing because the snow is making bonds when the little water molecules are bonding together in their snowflake, and heat is actually released and it warms the air up just a little bit. And then on top of that, the clouds act like a giant blanket and trap whatever heat that the sun put down in. So between the clouds and between the snow, it's actually going to be warmer than if it wasn't snowing. So if you're going to go Christmas caroling, I don't think it's ever going to snow, but if it ever snows, it's warmer than if it's not snowing. The worst is when there's snow on the ground, so it's all cold, and then the sky is clear, so you don't have that insulation, and it just gets really, really cold at night. So you guys are gonna play with this, and I hope that you can handle yourselves okay with my chemicals. Nothing super dangerous, but you do have to use goggles. Goggles are not optional. I kind of let some of you be a little lax with the goggles, Aiden, your glasses. These are not, this is not water we are doing with today. So you have to have your sides covered. So you have to have the for real safety glasses or the safety goggles. So even if you have glasses, it doesn't protect you from the side. So so you have to wear the goggles and make sure you check your temperatures. Don't change thermometers midway through. Our thermometers are sketchy and they weigh different compared to each other. So you're looking at the difference in temperature. So use the same thermometer so that it doesn't throw off your results. And then I want you to work on your review. If you come up with questions, then email me. I can help you. And oh my gosh, I had darn well stinking better be back tomorrow. And then we'll play a Kahoot tomorrow to help review for the test, and then we'll have the test. Okay. Anyway, let me know if you have any questions. Have fun. This is such a fun day, and I'm so sad I can't be there with you. I actually am working on a thing for my physical science class, so I've been making purified sodium acetate all weekend long. And it's been fun. They grew like little crystals. You have to check out my Facebook page. No, my YouTube page. There's a video. I spilled some of the sodium acetate solution on the burner in my stove and it grew crystals and it was pretty. And I took a video and it's like 30 seconds. And so go watch the sodium acetate crystals grow. And then there'll be awesome, way more coolness that I'm doing with the sodium acetate once I get that all figured out. Anyway, I will be there tomorrow. I hope I'm there tomorrow. And if I'm not, it's because I'm sick. Anyway, I'll talk to you later, guys. Bye.